some of you, dear contestants, are very young. So perhaps you do not know who is Professor Terence Tao. So just a few words of introduction. He participated at the AIMO for the first time when he was 11 years old, and he received a bronze medal. Next year, he came back and he received a silver medal. After that, at the age of 13, he received a gold medal, and he was the youngest participant to receive a gold medal. Then he, get bored, and he went to university, and he didn't participate at the AIMO anymore. Now he is a professor at the University of California, LA, and I can say that he is definitely the biggest AIMO star, and of course one of the most influential mathematicians of our time. Especially for you, Professor Terence Tao.
Thank you. I'm very happy to be back here at an IMO. The time I had at the IMO was one of the most fun times of my life. I still look back on it fondly. I hope you all had fun, not just in the competition, whether you get a good score or not, but also in the social activities. It was really, they always host a really good event here. So my talk is on AI and more generally machine assistance in mathematics. So you've all heard about AI and how it's changing everything. I think earlier today there was a talk by DeepMind on how they released a new product, Alpha Geometry, that can answer some IMO geometry questions now. And there will be a presentation on the AI Math Olympiad right after my talk, actually. So please stay after my talk for that. So I'll be talking more about how these tools are beginning to change research mathematics, which is different from competition mathematics. Instead of having 3 hours or whatever to solve a problem, you take months, and sometimes you don't solve the problem, then you have to change the problem. It is definitely not the same as math competitions, although there's some overlap in skills. So it's all very exciting, and it's beginning to be transformative. But on the other hand, there's also a sense of continuity. We've actually been using computers and machines to do mathematics for a long time, and it's just the nature, the way in which we're doing it is changing. But it actually is following on a long tradition of machine assistance. So here's a question. How long have we been using machines to do mathematics? And the answer is thousands of years. I mean, here's a machine that the Romans used to do mathematics. The abacus, one of the early machines. There's even some earlier ones. So that's kind of boring. So that's not a very smart machine. What about computers? All right. How long have we been using computers to do mathematics? That's about 300, 400 years. I think that's a bit weird because our modern computers we didn't have the electronic computers until the 1930s and 1940s. But computers weren't always electronic. Before that, they were mechanical, and then before that, they were human. The computer was actually a job profession, someone who computes. Here is a cluster of computers during the World War. To compute ballistics and other things, they had a whole cluster of computers who were usually girls because the men were off fighting the war. With lots of adding machines, and it was basically, there were programmers who basically just told the girls what to do, and the basic unit of computational power at the time was not the CPU, it was the kilogirl. It's a kilogirl hour. So how much computation you can do with 1,000 girls working like this for 1 hour. But we've been using computers actually even before that, as I said, since the 1700s or even earlier. The most basic use of computers in those times was to build tables. So you may have heard of the logarithm tables of Napier. If you wanted to compute sines and cosines and so forth, right, you used a computer to generate these huge tables. When I was still in high school, we still, in our curriculum, learned how to use these tables. They were just being phased out. because now we had calculators and now computers. We still use tables today. I mean, in mathematical research, we rely on tables. We call them databases now, but they're still the same thing. There are many important results in mathematics that were first discovered through tables. In number theory, one of the most fundamental results in number theory is called the prime number theorem. It tells you roughly how many primes there are up to a large number x. And it was discovered by Legendre and Gauss. They couldn't prove it, but they conjectured it to be true because Gauss and others, they basically had computers. In fact, Gauss himself was a bit of a computer, to compute tables of the first million primes and try to find patterns. And then a couple of centuries later, there's another really important conjecture. So the prime number theorem was eventually proven in like 1907 or so. But there's another really central problem in number theory called the Birchett-Swinton-Dye conjecture, which I won't talk about here. But it was also first discovered by looking at lots and lots of tables. This time, tables of data about elliptic curves. A table that lots and lots of mathematicians use now, including myself, is something called the Online Encyclopedia of Integer Sequences. Maybe you've encountered it yourself. So you may recognize many integer sequences just from memory. Like if I tell you the sequence 1, 1, 2, 3, 5, 8, 13, you know what that is. That's the Fibonacci sequence. And the OEIS is a database of like hundreds of thousands of sequences like this. Many times when a mathematician is working on a research problem, there is some natural sequence of numbers associated. Maybe there's a sequence of spaces depending on n, and you compute the dimension or how many, or the cardinality of a set or something. You can compute the first 5 or 6 of these or 10 of these numbers, put it, and then compare it into the OEIS. And if you're lucky, this sequence has already been put there by somebody else who has, and it came from it was discovered from a completely different source, coming from studying some other mathematical problem, and then that really gives you a big clue that there's a connection between two problems, and many promising productive research has come up that way. Okay, so tables are one of the earliest ways we've been using computers. Most famous, when you think of using computers to do mathematics, you think of number crunching. The formal name for this is scientific computation. So you want to do a very big calculation, and you just have to do lots and lots of arithmetic. You source it out to a computer. And so we've been doing that since the 1920s. Maybe the first person to really do a scientific computation was Hendrik Lorentz. So he was tasked by, I think, the Dutch to figure out what's going to happen. They wanted to build a really giant dike, the Athluisdijk. And they wanted to know what happened to the water flow. And so they had to model some fluid equations. And so he used a whole bunch of human computers, actually, to work this out. He had to invent floating point arithmetic to do this. So he realized that if you wanted to get a lot of people to do a lot of calculations very quickly, you should represent lots of numbers of different magnitudes as floating points. So, of course, we now use computers to model all kinds of things. If you're solving lots of linear equations or partial differential equations, you want to count some combinatorial, do some combinatorial calculations. You can also solve algebra problems. So, like in principle, like all the geometry questions, well, not quite all, but many of the geometry questions you see at Olympiads can be solved in principle by a scientific computation. There are these algebra packages that can solve. You can turn any geometry problem, say involving 10 points and some lines and circles, into a system of equations with, I don't know, 20 real variables and some 20 unknowns, and just whack it into, Sage or Maple or something. Unfortunately, once it gets beyond a certain size, the complexity becomes exponential, or even double exponential. And so until recently, it was not really feasible to just brute force these problems with just standard computer algebra packages, but now with AI assistance, maybe it's more promising. So you heard her talk about that this morning. Another type of scientific computation that has become quite powerful is what are called SAT solvers, satisfiability solvers. So these are meant to solve kind of basically they solve logic puzzles. Like if you have 10 statements or maybe 1,000 statements that are true or false. And you know that maybe if the third statement is true and the sixth statement is true, then the seventh statement must be false. And if you're given a whole bunch of constraints like that, a SAT solver will try to take all this information and conclude, can you prove a certain combination of these sentences or not? And then there's a more fancy version of a SAT solver called a SMT solver, satisfiability modular theories, where you also have some variables, X, Y, and Z, and you assume some laws like maybe there's an addition operation, and addition is commutative and associative. And you plug in these laws as well as some other facts, and you try to just brute force, can you deduce some conclusion out of some finite set of hypotheses? So those are quite powerful, but unfortunately they also scale they don't scale well at all. Again, the time complexity to solve them grows exponentially, and so once you get past 1,000 or so propositions, it becomes really, really hard for these solvers to actually run in any reasonable amount of time. But they can actually solve some problems. So one recent success, for example, here's a problem in combinatorics, which probably will only ever be solved by computer. This will not be possible to solve by a human, I think, unassisted. So it concerned what was called the Pythagorean triple problem, which was unsolved until this big computer SAT solver calculation. So the question is, you take the natural numbers and you color them two colors, red or blue. And the question is it true that no matter how you color these two the natural numbers, one of the colors must contain a Pythagorean triple, ABC, three numbers that which form the sides of a right-angle triangle, like 3, 4, 5. And so this was not known to be true. We have no sort of human proof of this. But we have a computer proof. It is now known that, in fact, you don't need all the natural numbers. You just need to go up to 7,824. That no matter how many ways you can color 7,824 into two color classes, one of them will contain a Pythagorean triple. Now, there's 2 to the 7,824 such classes. You can't do it by brute force. Okay, so you have to be somewhat clever, but it is possible. And then if you do, okay, and then if 7,825, sorry. So once you have 7,825, you must have a Pythagorean triple. There was an example of 7,824 where there's no Pythagorean triple in either class. So that's provable. It actually, I think it's the at the time it was the world's longest proof ever. I think now it's the second longest proof. The proof required 7 CPU years of computation, and it generated a proof certificate. So the actual proof is 200 terabytes long, although it's since been compressed to a mere 86 gigabytes. So this is one way in which we're using computers just to do basically enormous case analysis. Okay, so that's a sort of fairly obvious way to use computers. But in recent years, we're beginning to use computers in more creative ways. So there are 3 ways in which computers are being used to do mathematics, which I think are really exciting, particularly when they are combined with each other and with the more classical databases, tables, and symbolic computation, scientific computation. So first of all, we're using machine learning, neural networks, to discover new connections and just find out ways in which different types of mathematics are correlated in ways that you would not see as a human, or unlikely to see as a human. Most splashily, there's large language models, which are, in some sense, very large versions of machine learning algorithms, which can take natural language, like ChatGPT and Cloud and so forth, and they can sometimes generate possible proofs, approaches to problems, which sometimes they work, sometimes they don't. You'll see a bit more examples of this actually in the talk after mine. But then there's also another technology which is just becoming usable by the everyday mathematician, which are called formal proof assistants. So these are languages. So computer languages you're used to using to write executable code, programs that do things. Formal proof assistants are languages that you write to check things, to check whether a certain argument is actually true and actually gives you the conclusion from the data. And these have been fairly annoying to use until very recently, and they're becoming now somewhat easy to use, and they're facilitating a lot of interesting math projects that wouldn't have been possible without these proof assistants. And they will combine very well in the future with the other tools I described here. So I want to talk about sort of these more modern ways to use machines and computers to do mathematics. So I think I started with proof assistants. Yeah, so the first really computer-assisted proof, maybe in history, was the proof of the 4-color theorem. Every planar map can be colored in using only 4 colors. That was proven in 1976. This was before proof assistance. There wasn't really, it wouldn't really be called a computer proof nowadays. It's a proof which, it was a massive computation, like half of which was done by a computer and half of which was done by humans. The way they prove the four-color theorem is that you basically induct on the number of countries, and you show that if you have a massive map, there is some subgraph of countries. There's produced a list of about 1,000, 2,000 special subgraphs, and every big graph of countries had to contain, in some sense, one of these subgraphs. That was one thing they had to check. And then they had to check that every time you had a subgraph, you could replace that subgraph with something simpler. And if you could four-color the simpler thing, you could color the main thing. And you had to check these properties. I think they're called dischargeability and reducibility for each of these 1,000 or so graphs. I think one of these tasks they could do by computer, although this was a 1970s computer. I think they had to enter in each graph by hand into this one program and check it. The other task was actually done by a human computer. One of the daughters of one of the authors actually had to spend hours and hours just manually checking this. I think the reducibility thing. It was very tedious. And the process was not perfect. There were lots of little mistakes, and they had to update the table. So it was not, by modern standards, a computer verifiable proof. That came much later in the 90s, where there was a simpler proof using a mere 700 or so graphs. But now all the things that need to be checked, it was a very precise, well-defined list of properties, and you could write code in your favorite computer language, C or Python or something, and you can check it in a couple pages, in a couple hundred lines of code, in like a few minutes with a modern computer. And then to actually check that is completely to write a proof that goes all the way down to the axioms of mathematics, that was done in 2005 using a proof assistant language called Koch. I think it's now it's renamed Roch. So that was one of the first proofs. And we see there's a huge gap between sort of when the proof first appeared and then when we actually could completely verify by computer. Another famous example is the Kepler conjecture for sphere packing. This is a really old conjecture of Kepler from the 17th century. It's very easy to state. You take a whole bunch of unit spheres, and you want to cover three-dimensional space as efficiently as possible. So there's sort of an obvious way to try to pack spheres. It's a triangular packing. Like the way you pack oranges at a grocery store. There's also a dual packing called the cubic packing, which has the same density. So there's a density of about 74%, which is sort of the obvious packing. And the question is that the best possible? And this turns out to be a surprisingly hard problem. In 2 dimensions, the hexagonal packing is not too hard to show. It's the best. Only very recently, in 8 and 24 dimensions, do we know the answer as a great work of Yosovska. Maybe she talked about it yesterday. But 3 was 3 is the only other case that we know of, except for 1, which is trivial. But yeah, it was surprisingly difficult to prove. Again, there was no completely human readable proof of this conjecture. There is a strategy. So of course the problem is that there's infinitely many of these of these spheres, and the density is an asymptotic thing. So it's not a priori a finite problem that you can just throw at a computer. But you can try to reduce it to a finite problem. So there's a strategy proposed by Toth in the 50s. So every time you have a packing, it subdivides space into these polyhedra called Voronoi regions. Okay, so the Voronoi polytope of a sphere is just all the points which are closer to the center of that sphere than to all the other spheres. Okay, so you can sort of split up space into all these polytopes, and these polytopes have certain volumes. You can also count their faces and their surface areas and so forth. And so they all have these statistics. And the volumes, like the packing density, is very closely related to sort of the average volume of these regions. So if you can say something about kind of how these volumes of these polytopes behave on average, then you could get at least maybe some upper bound onto how efficient these packings can be. And you can try to make relations between these polytopes. Like if one polytope is very big, maybe this forces the nearby ones to be very small. And so maybe you can try to find some inequalities connecting the volume of one Voronoi cell to another. And so Tao proposed maybe we should just collect lots and lots of these inequalities and then do some linear program or something, and hopefully you can just derive the right bound of this magic pi over 3 of root 2, which is the right density, from all these inequalities. So people tried this. There were many attempts. Some even claimed success, but none have been accepted as actual proofs. The problem was eventually solved first by Thomas Hales and his co-authors. He did basically the same strategy, but using there are lots of technical tweaks. He changed the cells from Voronoi cells to slightly more fancy cells. And instead of taking the volume, he invented this thing called the score that you assign to each of these. It's the volume plus or minus lots of little ad hoc adjustments. But again, with the aim of trying to create all these linear inequalities between these different scores, and to eventually get upper bounds of the density and to hopefully hit exactly the optimal density. It's a very flexible method. Actually, it's sort of too flexible because there's too many things you can try. There's so many ways you can set up the score and so forth. So there's a quote here. So Samuel Ferguson was the co-author. Sorry, I forgot the name. So Hales and Ferguson realized that every time he encountered problems in trying to minimize his functionals and so forth, he could just change the score and try it again. But then all the things that they checked already, they had to redo. And so the scoring function became more and more complicated. They worked on this for almost a decade, I think, and it became more and more complicated. But with each change, we cut months or years from our work. This incessant fiddling was unpopular with our colleagues. Every time I presented my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what I did in earlier papers, and this required going back and patching the earlier papers. But they eventually did it. So in 1998, they announced that they had finally found a score which obeyed a whole bunch of linear inequalities and in 150 variables, which they minimized and got their thing. Initially, they did not plan to make this a computer-assisted proof, but as the project became more and more complicated, it was inevitable. They had to use more and more computers. The proof was enormous by the standards of 1998. It was 250 pages of notes and 3 gigabytes of computer programs and data. It actually had a very tough time getting refereed. It got sent to the top journal of mathematics, one of the top, the Annals of Mathematics. And it took 4 years to referee with a panel of 12 referees. And at the end, they said they were 99% certain of the correctness of the proof, but they could not certify the correctness of the computer calculations. And they did a very unusual thing, actually, is that they published the paper with a little caveat from the editors saying this. They have since removed that caveat, actually. At the time, there was a lot more controversy as to whether a computer-assisted proof qualified as an actual proof. Now, I think we are much more comfortable with it. But even after it was published, there was doubt about whether it was really a proof. So this was maybe the first major high-profile problem where there was really a big incentive to really formalize this in a completely, all the way down to first principles in a formal proof language. And so Hales, in fact, created a language, a modification of existing languages to do this. He called it the FlySpec project. He estimated it would take 20 years to formalize his proof. But actually, with the help of 21 collaborators, he actually finally, in a mere 12 years, it finally appeared in 2014. So we now have sort of complete confidence in this particular result. But it was quite a painful thing to do. So moving now to, in the last few years, we've now figured out sort of a better workflow for how to formalize. It's still tedious, but it is getting better. So Peter Schulze, who is a very prominent young mathematician, Fields Medalist, for instance. So he's famous for many things, but he created this amazingly promising area of mathematics. It's called condensed mathematics. It deploys the power of algebra, category theory, and all the tools from algebra to apply to functional analysis, the theory of function spaces like Banach spaces and so forth, which an analysis has really been resistant to the method of algebra. But this area of mathematics, in principle, could allow one to solve questions in at least functional analysis, certain types of questions, with algebraic methods. So he set up this whole category of these things called condensed Abelian groups and condensed vector spaces. It would take too long to explain what condensed means. He basically, his thesis is that all our categories of function spaces that we learn in our graduate classes are incorrect, or they're not the natural ones. They're ones with better properties. So he set up this theory, but there was this one very important vanishing theorem which he needed to prove. So I've stated it here, but I'm not going to explain what any of these words mean, or the symbols mean. But there was a very technical vanishing of a certain category theoretic group that he needed to compute. And without this, the whole theory doesn't have any interesting consequences. So this was sort of a foundation of his theory. So he wrote a blog post about this result. He said he spent a whole year getting obsessed with the proof of this theorem, going almost crazy over it. In the end, we were able to get an argument put down on paper, but no one has dared to look at the details of this, so I still have lingering doubts. With this theorem, the hope that this condensed formalism can be fruitfully applied to functional analysis stands or falls. This theorem is of the utmost foundational importance, so being 99.9% sure is not enough. He said he was happy to see many study groups on condensed mathematics throughout the world, but they all stopped short of the proof of this theorem. This proof is not much fun, so he says this may be my most important theorem today, better be sure it's correct. So he was also very incentivized to formalize this theorem. Now in a more modern language, proof assistant language called Lean. So Lean is a language that has been developed quite a lot in recent years. There's a crowdsourced effort to develop this massive math library. So rather than deriving everything from the axioms of mathematics, which becomes very tedious the more advanced you go, and this type of mathematics is very advanced. So there's a central math library in Lean that can sort of, that has already proved lots of intermediate results, like the type of things you would see in, say, an undergraduate math course, like, say, the fundamental calculus or basic theorems of group theory or topology, and so forth. These have already been formalized, and so you have a standing base. You're not starting from the axioms, you're starting from roughly a undergraduate level math education. Still a big gap to where you need to go, but it helps. In order to formalize this, they had to add many extra. So the math library was not complete. It's still not complete. There's lots of areas of mathematics, listed some homological algebra, sheaf theory, topos theory, that needed to be added to this library. But in a mere 18 months, they were able to formalize this theorem. And the proof was basically correct. There were some minor technical issues, but nothing really major was discovered. They found some nice simplifications. There were some technical steps that were just too hard to formalize, and so they were forced to find some shortcuts. But actually, the value of this project was more indirect. Firstly, they greatly added to Lean's math library. Okay, so now this math library can handle lots of abstract algebra to a much greater extent than it could before. But also, there was other supporting software that got set up that future formalization projects have started using, including some that I did. So, for example, one tool that was set up as in the course of this project was what's called a blueprint. So, taking a huge, like 50-page proof and trying to directly formalize it is really painful. You have to keep the whole proof in your head. But so what we've realized is the right workflow is that you take a big proof, you apply, you first write what's called a blueprint, which sort of breaks up this proof into like hundreds of tiny little steps. Each step you can formalize separately, and then you just put them all together. So you try to break up a huge argument into lots of little pieces. And so you write that first, and then different people in your team can formalize different parts of different steps of your argument. So they also, as a byproduct of this formalization, they also wrote a very nice blueprint. This is why if you actually want to read the proof as a human, the blueprint is probably the best place to go to now. Another spin-off of this, so there's now also this formal proof, which is tens of thousands of lines long, but now there's efforts to try to convert that back to a human readable proof. So another thing that's been developed is that there are now tools that you can take a proof that's been written in, say, this language Lean. So here's an example where there's a proof written of a topological problem, and they converted it back to human readable proof. So all this text here is a proof that is computer generated from a formal proof. So it looks like a human proof. It uses the same sort of math language, but it's much more interactive. You can click on any location. I can't do it because it's a static PDF, but you can click on any location here, and it will tell you wherever you are, what are the hypotheses, what you're trying to prove, what's the variables. If there's a step that is too short, you can expand it, and it will explain where it came from, and you can go all the way down to the axioms if you want. I think this is a great, I think in the future textbooks will be written in this interactive style. You formalize them first, and then you can have much more interactive textbooks than currently. Inspired by this, I myself started a project to formalize. Last year I solved a problem in combinatorics with several other people, including Tim Gowers, who's here in the audience. So it's a problem in combinatorics. It's not super important what the problem is. Okay, there's a subset of an energy 2 cube. So think of ZMOD 2 to the end, like what's called a Hamming cube, and it obeys a property called small doubling. Then there's a certain limit to how big it can be. Okay, but it doesn't really matter what the statement is. But it's a combinatorial statement. We proved it. The proof is about 33 pages, and we formalized it in a relatively record. Actually, it's probably still the fastest formalized actual research paper. In 3 weeks in a group project of about 20 people, using all this blueprint machinery that had been developed in Schultz's project. So basically, and it makes the task of proving things much more open and collaborative, and you get all these nice visualizations. So as I said, the first thing you do is that you take your big theorem and you break it up into lots and lots of little pieces. So the theorem that we have is we call it PFR. I won't explain why. That corresponds to this little bubble at the bottom of this graph here, and then we introduce all these other statements, which and so like the proof of PFR has to depend on several other previous statements, and then these ones depend on previous statements as well. So there's this dependency graph, and they have different colors depending on whether you formalize them or not. So a green proof is a green bubble is a statement that you've already formally proven in your language. A blue bubble is one that hasn't yet been formalized but is ready to be formalized. Like all the definitions are in place. Someone needs to actually go ahead and do it. And a white bubble, even the statement hasn't been formalized yet. Someone has to write in the statement. So you get this tree of tasks. And then the beauty of this project is that you can get all these people to collaborate on different pieces of this graph independently. So every little bubble corresponds to some statement, and you don't need to understand the whole proof in order to just work on your little piece. So you can so this was a problem in combinatorics, but the people who contributed, there were people from probability, there were people who were not even mathematicians, they were computer programmers, but they were just very good at sort of doing these little mini puzzle type things. And so everyone just sort of just picked one bubble that they think they could do, and they did it. And yeah, in 3 weeks we did the whole thing. It was a really exciting project. And in mathematics we don't normally collaborate with this many people. We collaborate, maybe 5 people is the most I've normally seen. It's because when you collaborate on a big project, you have to trust that everyone's math is correct. And past a certain size, this is just not feasible. But with a project like this, this Lean compiler just automatically checks. You cannot upload anything that doesn't compile. It will get rejected. So you can collaborate with people that you never met before. I met a lot of people. I actually wrote a lot of letters of recommendation actually coming out of this project. And this is some of an example. Like this is like one little piece of the proof, and so this is what a proof looks like in Lean. It's not exact. I mean, if you know the language, it's human readable, but it looks a little bit unusual. But it really sort of decouples the task of proving things into many different sort of disjoint skills. You can have some people who see the big picture and sort of organize things into little pieces, and then you have people who don't necessarily know all the mathematics, but can just work on little pieces at a time. So I think this will be a more and more common way of doing mathematics going forward. It still is painful to do. Like the tools are not really they're getting better and user-friendlier, but you still need to have like some expertise in programming. I would say it takes maybe 10 times longer to formalize a proof than to write it by hand. On the other hand, if you want to change a proof, so for example, there was a number 12 that showed up in this theorem. We later improved this 12 to an 11. We got a slightly stronger theorem. And normally, if you do that, you have to rewrite the whole proof. Or like you could maybe cut and paste 12 to 11, but then you have to check you didn't make any mistakes when you did that. But actually, when we formalized this, then we got the improvement. It only took a few days to change the 12 to 11. We just changed the 12 to 11 somewhere, and then the compiler complained at like 5 different places. Now this very specific parts of the proof were not working, and we could just do some targeted fixes. So in fact, so already for some specific types of doing mathematics, actually already the formal approach is actually faster. So now there are actually quite a few big proof formalization projects going on right now. Maybe the biggest is Kevin Buzzard's project. He's just got a big grant to formalize Fermat's last theorem into Lean. He says it will take 5 years to do the most important parts of this proof. He doesn't claim to do the whole thing in 5 years, but that'd be an interesting project. It's already got started. It's already underway, actually. So that is formal proof assistance. Talk about machine learning. So machine learning, so these are using neural networks to predict answers to various questions that you can use in many ways. I think I'll skip the first way I was discussing it, which is to use neural networks to guess solutions to partial differential equations, which is a very exciting new tool in PDE, but I will skip it. I would instead talk about another application of machine learning to knot theory. So knot theory is quite a fun area of mathematics. It's an interesting area that it brings together many different fields of mathematics, and they don't really talk to each other. So a knot is just a loop of string or a curve really in space that is closed, and two knots are equivalent if there's some way to continuously deform one knot to another, which in a way in which you're not allowed to cross. The string is not allowed to cross itself. Okay, and so. The basic questions in knot theory are when are two knots equivalent? Okay, if I give you two knots, is there some way to turn one into the other? And the way you approach this question normally is that you develop these things called knot invariants. So these are various numbers, sometimes also polynomials, that you can attach to a knot, and these numbers don't change no matter how you continuously deform the knot. So if two knots have different invariants, they cannot be equivalent. So there are many types of knots, of invariants. There's something called a signature, which sort of counts, you flatten the knot and you count crossings, whether the crossings go over or under, and you create a certain matrix and so forth. And there's a certain integer called the signature. So that is one type of knot invariant. There's some famous polynomials called the Jones polynomial and the Helmholtz polynomial, which are connected to many areas of mathematics, but I won't talk about. And then there's these things called hyperbolic invariants, which come from geometry. You can take the complement of the knot, and that is actually what's called it's usually a hyperbolic space. It comes with a certain geometric structure. It has a notion of distance, and you can keep it as volume and some other invariants. And so these are invariants that are real or complex numbers. And so every knot comes with some combinatorial invariants like signatures, and it comes with these geometric invariants like these hyperbolic invariants like So here is a whole list of knots with various of the hyperbolic invariants. There's something called the hyperbolic volume and the homological cusp shape and so forth. And these are real and complex numbers. But no one knew of any link between these two. So there are these two separate ways to create statistics of knots, and there was no connection between them. So it was only very recently that people started using machine learning to attack this problem. So they created databases of millions of knots, which actually was already a slightly non-trivial task. And they trained a neural network on this. And they found that after training the neural network, you could give it all the hyperbolic geometry invariants, and like 90% of the time it will guess the right signature. So it created this black box, and it will tell you how the signature was somehow hidden somewhere in these geometric invariants. But it didn't tell you how. It was this black box. But that's still useful, because once you have this black box, you can just play with it. So what they did next is actually a very simple analysis. It's what's called saliency analysis. So what this black box does is it takes about 20 different inputs, one for each hyperlink invariant, and produces one output, the signature. So once you have this black box, you can just tweak each input. You just say, oh, what if I change one input? How likely is it to change the output? And of the 20 inputs that they found that only 3 of them actually had played a really major role in the output. The other 17 were barely relevant. And it wasn't the 3 that they expected. Okay? They expected the volume, for example, to be very important, and the volume turns out to be almost irrelevant. There were 3, something called longitudinal translation and the real and complex parts of meridional translation. So there were these 3 invariants that were the most important. So once they identified the ones that were most important, they could just plot directly the signature against those 3 particular inputs, and then they could eyeball rather than use a neural network. They used a human network to then see, oh, okay, there's some obvious patterns here, and so by staring at these graphs, they could actually make conjectures as to what was actually going on. So they made a conjecture based on this, which turned out to be wrong actually, but. They actually used I think they turned back to the neural network to actually show that it was wrong. But then the way that it failed, they could correct it. And they found a corrected version of their conjecture, which actually did explain this phenomenon. And then once they found the right statement, they were able to prove it. So they actually have a theoretical explanation of why the signature is so closely related to these particular statistics. So this, I think, is a way in which machine learning is being increasingly used in mathematics. It doesn't directly solve the problem for you, but it gives you all these really useful hints as to what the connections are and go where to look for them. But you still need the human to actually make the connections. And then finally, we have the large language models, which are the most splashy and made the most news. Neural networks have been around for 20 years, but language models have already also been around five or so years, but they've only become sort of human level in output very recently. So you've all probably heard of GPT-4. This is ChatGPT's current model. Very famously, when GPT-4 came out, there was a paper describing its capabilities, and they fed it basically a question from the 2022 AIMO. There's a slightly simplified version. If you studied the 22 AIMO, you probably don't. It's not exactly the same form, but it's a simplified form. And for this particular question, actually, you give it the question, and it actually gives a complete correct solution to this question. It actually solved an AIMO question. Unfortunately, this is an extremely cherry-picked example. I think they tested hundreds of AIMO level questions, and I think they had a success rate of about 1%. So this particular problem they were able to solve, and they had to format the problem in the right way to get the solution. But still, this is quite amazing. On the other hand, the funny thing about these tools is that things that humans find difficult, AI can do very easily sometimes, but things that humans find easy, AI often struggles with. It is a very orthogonal way of solving problems. In a very related paper or presentation, they asked the same model to do a basic arithmetic computation, 7 times 4 plus 8 times 8. And the model, which is just guessing the most likely output based on the input, basically just guessed, the answer is 120. And then it paused and said, okay, maybe I should give an explanation why it's 120. So they did a step-by-step. But when they did a step-by-step, they actually arrived at the actual answer, which is 92, and not the answer that they originally started with. So then if you asked, wait, but you said that it was 120, and they said, oh, that was a typo, sorry. The correct answer was 92. So they're not solving the problem by first principles. They're just sort of guessing at each step of the output what is the most natural thing to say next. And the amazing thing is sometimes that works, but often it doesn't. And it's still, it's still ongoing how to sort of make it more accurate. So people are trying all kinds of things. You can connect these models to other more reliable software. In fact, you will see a presentation after where there's a large language model connected where you don't do the computation yourself. You outsource it to Python in that case. But another thing you can do is that you can force the language model to only produce correct answers by forcing the model to output in one of these proof-assistant languages. And if it doesn't compile, you send it back to the AI, and the AI has to try again. Or you can try to teach it directly the same problem-solving techniques I use to solve AIMO problems. Try simple examples, prove a contradiction. Try to actually prove step by step and so forth. So people are trying all kinds of things. It's still nowhere near. Well, okay, we're not near able to solve a large majority of, say, math Olympiad problems, let alone math research problems. But we're making progress. Besides being able to actually solve problems directly, actually it's also useful to just as a muse. Actually, I've also used these models myself. I've experimented with various problems. I had a combinatorial problem which I was trying a few things and they weren't working. So as an experiment, I just tried asking GPT, what other techniques would you suggest to solve this question? And it gave me a list of 10 techniques, of which like 5 of which I'd already tried, or were obviously not helpful. Well, yeah, a couple were not helpful. But there was one technique I'd not tried, which was to use generating functions for this particular question, which once they suggested it, I realized it was the right approach, but I had missed it. So I just as someone to converse with, it is somewhat useful. It is not great right now, but it is not completely useless. There's another type of AI assistance that actually become very useful for proof assistance. Actually, as I said, writing formal proofs is a very tedious task. I mean, it's like any really fussy computer language. You have to get the syntax exactly right. If you miss a step, it doesn't compile. But there are tools. So I use something called GitHub Copilot, where you can write down half of a proof, and it will try to guess what the next line is. And about 20% of the time, it actually guesses something close to being correct. And then you can just say, I'll accept that, and say, okay. So in this case, I was trying to prove the statement here, and the lines in gray are the ones that Copilot suggested. It turns out the first line is useless, but the second line, which you can't quite see, actually did solve this particular problem. So you still have to. You can't just accept. Can't accept the input because it won't necessarily compile. But if you already know sort of how the code works, it saves you a lot of time. So these tools are getting better. So right now they can maybe, like, if a proof is 1 line or 2 lines long, they can fill it in automatically. There are now experiments to sort of iterate an AI suggesting a proof, and then you feed it back to the compiler, and then if it compiles wrong, you send the error message back, and we're beginning to sort of proofs that are like 4 or 5 lines long. They can begin to find by this method. Of course, a big proof is like tens of thousands of lines, so it's nowhere near the point where you can just sort of instantly get your proof formalized immediately. But it is already a useful tool. Okay, so where are we now? So there are people who are hoping that in a few years we can use computers to actually solve math problems directly. I think we are still a long way away from that. For very narrowly focused problems, you can sort of set up specialized AIs to handle just a very narrow band of problems, but even then they're not fully reliable. They can be useful, but still, So for the next few years, at least, they're basically going to be really useful assistants, and beyond the sort of the brute force computational assistance that we are already familiar with. And people are trying all kinds of creative things. I think one direction which I find particularly exciting, hasn't really been successful yet, is that hopefully these AIs become very good at generating good conjectures. Like if you want, so we already saw a little example of this with the knots, where they could already sort of conjecture those connections between 2 different statistics. So there's just the hope that you just create these enormous data sets and feed them into an AI, and they will just automatically generate lots of nice connections between different mathematical objects. This hasn't really been, we don't really know how to do this yet, partly because we don't have these massive data sets. But I think this is something that would eventually be possible. One thing I'm also excited, this is a type of mathematics that just doesn't exist yet. Right now, because proving theorems is such a painstaking process, we prove 1 theorem at a time, or maybe 2 or 3 if you're efficient. But with AIs, you could imagine in the future, instead of trying to solve one problem or something, you take a class of 1,000 similar problems, and you say, okay, you tell your AI, try to solve these 1,000 problems with this technique, and it will report back, oh, I could solve 35% of these problems with this technique. What about this technique? Then I can solve this percentage of problems. Well, if I combine them, I can do this. You could start exploring the space of problems rather than just each problem separately. And this is something that you either cannot do right now, or you do over a process of decades with, with dozens and dozens of papers, slowly figuring out what you can and can't do with various techniques. But with these tools, you could really do. You could really sort of start, doing mathematics on a scale which is really not really unprecedented. The future is going to be really exciting, I think. We will still also be proving theorems the old-fashioned way. In fact, we'll have to, because we won't be able to guide these AIs unless we also know how to do these things ourselves. But we'll be able to do lots of things that we can't do right now. Okay, I think I will stop there. So thank you very much. Yeah. So we are on a tight schedule, but I was told we have time for maybe 3 or so questions. So if people would raise hands, and there's someone over there.
Thank you. Can you hear me? Thank you. That was a beautiful talk. I particularly loved about formalizing mathematics. But one thing that you didn't mention was Voevodsky, who left algebraic geometry because he made a mistake and started formalizing homotopy type theory. I would be interested to know if you have studied this and have any comments on it.
Right. So Voevodsky, he was worried about a crisis in certain areas of mathematics, including some that he created. The proofs were so abstract and sophisticated that there was no way to verify that they're completely true. So he proposed changing the foundation of mathematics to homotopy, a high-order homotopy type theory, which is more robust. Like if you change the underlying axiom of mathematics, a lot of what you prove, in this theory is still true. There are proof-assistant languages that are based on this sort of homotopy type theory. Lean is not actually by design, because Lean wants to formalize a lot of traditional mathematics, which is not written in this language. I do hope in the future there will be multiple proof-assistant. There are multiple proof-assistant languages with different strengths and weaknesses. One thing that is not we don't have right now is automatic ways to translate a proof in one language to another. That's actually one place where AI, I think, will be very useful. Once we have that, then we can if you have a different philosophy of your foundation of mathematics, hopefully we can just translate a proof that has been formalized in one language to another, and then everyone will be convinced, including Voevodsky if he was still alive, hopefully. So there are multiple approaches to formalizing mathematics, and we shouldn't just fix on one particular standard just yet. Okay. It's sort of a random process, but okay.
That will not be quite relevant to the topic of the talk. But I was recently applying for PhDs, and the advice I was given by the professors was basically along the lines of the longer the better. So it seems like there's kind of a general agreement that mathematicians need somehow it would seem to me, grow up to big ideas. So from that perspective, how do you think about your decision about going to the university at such a young age? Did you think how it influenced you as a mathematician and as a human being? And
I had some very good advisors, both as at the high school and undergraduate and graduate level. I don't think it's a race. You go to university when you're ready to go. you shouldn't go just because you were told you need X years or something to do this. I think it's different for different people. It was very important for me. I went to undergraduate when I was 13, but but at a university that was very close to where I lived. So I lived with my parents, and they drove quite a lot actually to the university for all my classes. If I didn't have that, I don't think I would have had a good experience. So it really depends. I did my university at a very young age. Doesn't mean that everybody should do that. There's no single answer to this question.
Thank you.
Okay.
So another kind of more general question. Given that you've contributed to truly myriad mathematical fields, how do you go about choosing your next research topic and problem you want to solve? And also, what's your Erdos number?
Okay, well, my Erdos number is 2, that's easy. But I actually don't know. Early on in my career, I had advisors who would suggest problems to me. Nowadays, often it just comes by serendipity. Math is a very social activity. You go to lots of events. So, after this AIMO, I'm going to a math conference in Edinburgh. I'm going to talk to a lot of people in actually area connected to this PFR conjecture thing, actually. And likely I'll have some interesting math conversations, and maybe some research question will come out of it. I do have some long-term projects that I would like to, something that I'd like to solve, but increasingly I find that it's the questions that just sort of come up by conversation with other mathematicians. I didn't know I'd be talking so much about AI actually until about 2 years ago, for instance. I think you should be sort of, the future is going to require more flexibility, and there will still be people who will specialize in one topic and just one topic and be the world expert in X. But increasingly, I think there will be more and more people who will move around over time, and just they will find interesting new mathematics every few years just by talking to other people. Okay, I think we have to move on, actually. So the next speaker is Simon Coyle from XTX, who will talk about the AI Math Olympiad.